about robot world models. Now, before we talk about robot world models, let's talk a bit about the robot. We are going to be working with the droid embodiment, which is basically this Franca robot with two external stereo cameras and a wrist-mounted camera. And most of the takeaways that I describe in this talk will be valid for any kind of robotic embodiment, but most of the ones that I focus on will be on these. Why? Because Droid is actually this distributed kind of data collection that was done across a large number of institutions, and it has all kinds of unconstrained environments, mostly indoors, but sometimes there are a few outdoor environments as well. So let's begin with the big question: what is a world model? Well, the way I define it is that a world model is this machine that takes as input the initial state and action conditioning, and then the world model processes that to predict the future. And for most intents and purposes, these actions could be both high level and low level. And surprisingly, we have actually been building these world models for a really long time. And those are simulators. And simulators are kind of like a world model because they take a current state as input, some action, and then they're able to simulate the future. The one issue with simulators, though, is that they're quite handcrafted and they have this like huge sim-to-real gap. So either their control is not aligned, well, in these cases, all of these control is quite aligned, but sometimes the visuals are off. And yeah, in general, they have these sim-to-real gaps. And most of the time, they're used for simple tasks. But the question then comes out to be, how do we simulate these more complicated tasks? Like something like cloth manipulation, where you can see that the robot is either wiping the table or picking up that cloth and placing it on this, I would guess, board or something. So what's the solution? Well, one solution that you can do that everybody else in machine learning has seen that works is to use data to learn a simulator. And the emerging technique is to use a video diffusion model for these. So this is the same slide that I showed before. And what changes here with the video diffusion model is that the world model gets replaced by a video diffusion model. The input state gets replaced by an input frame. The action remains the same, but now we're predicting the future frames, which is basically a video. One such example of this is Control World. It's made for the Droid embodiment. And how it works is it takes the three, like it's a multi-view setup, so it takes the three input frames, the action conditioning, and then it fine-tunes this huge stable video diffusion model to predict the future. And this is what they're showing over the time that it shows the video. And they work so well that what you actually saw was not a real video, that this was fully generated with the world model. So this is not actually a real video. Now, why do we need it? Well, because AI is not perfect. And you'll start to see that there are a lot of mistakes and misunderstandings that we can't get rid of. In the digital world, you can basically click undo and it would go back. But in the real world, you can't. And we can see in this case that it fails, and now you have to go and clean this place. So the question is, then can we do this? Can we run this entire robot trajectory before deploying it? So can we like test it on a digital setup? For simple tasks, we can use simulators. So this is like pick banana and place it in the box, which I think they work quite well, and simulators are quite good at replicating these kind of things. But for the more complicated ones, we would need to use a world model. And for those, we need these closed loop inferences, which would basically take the input frame, predict the video, and then it would go back as input, and then it would go ahead again. And the catch is that these video models work well when this is a very short sequence, but when you start making it run for long, they start to degrade. So here is the reference, and you can see that the entire arm is gone, and it's completely messed up. And in this case, you can see even more interestingly, or if you didn't catch it, the entire bowl disappears, and you can see it go away. And for any downstream task that would use any of these generated video for any kind of thing, like for example, if you attached a VLM to check for task completion, if the main object itself disappears, it's impossible to run that task. So we think that this happens due to exposure bias, which is basically that the model was never trained on seeing its own frame as input, and therefore it's unable to continue from there. And this is what we kind of address in our first work, which is PersistWorld. And the idea is to train the model on its own autoregressive rollouts. This is the paper that I did with Patrick, Josef, and Vlado, and it's accepted at ECCV this year. And to talk about it, we would like to, to begin with, we need to generate the autoregressive rollout. And that happens this way. You take your input, you pass it to a policy that generates an action, that goes to the world model, that generates something else, that again goes to the policy, that again generates some action, that goes on again and again and again, and you can do it as many number of times. You do it anywhere from 5 to 10 times. And once you end up getting this corrupted history, we do this RL-style post-training. And similar to most modern RL post-training strategies, it happens in 2 stages. In the first stage, we are trying to just generate like samples. And how that works is we take our corrupted history buffer, we pass it to a world model, and we generate K future samples. This is like a GRPO style K future continuations for this action. Then we take our K continuations, and then we score and we rank them. For us, because we have the ground truth trajectory, we can kind of just look for visual metrics and visual similarity. But there are other kinds of things that I've seen people do recently, like using JEPA models for physics and more interesting things on top. So something like this, you would have like the history buffer, the model would generate K rollouts, and because you have the ground truth, you can kind of look at the reward. So once you've collected your samples, the idea is that you do some kind of a GRPO style training, but it's a bit different because this is like a contrastive training. You have to do something like this for diffusion models since it's really inefficient to backpropagate throughout the entire diffusion trajectory. And for an overview of the insight, what it does is you can kind of like imagine that it's relabeling these collected trajectories. And it says that, okay, the ones that are really good generate more samples like that, and the ones that are really bad don't generate samples like those. So kind of like this, you can imagine that if your sample has a high reward, this is your model, it's pulled towards this direction, effectively pulled towards this. If the reward is kind of okay, it's kind of just set to stay at your old position. And if it's also bad, it's still being pulled towards, or rather being pushed away from it. So this kind of works quite well. And when we look at the results, we see that our method improves over all the previous methods. And specifically, compared to control world, we are able to improve by quite a bit, by almost 1.5 PSNR on these visual metrics. So SSIM, PSNR measure like your pixel level similarity, so things like whether there are like lighting and other things that are same. And these LPIPs are the ones that check more human-aligned things like edges and other perceptual metrics. And we see that this improvement is both on the external cameras and the wrist cameras. And the wrist camera is generally a bit worse because it is a more dynamic scene, so it's going to be a bit harder. And yeah, I think I would also like to mention that these metrics are actually calculated by running a long rollout. So we do this closed loop inference that I was talking about, and we run it for almost 10, 20 seconds, and then we basically measure these values on that. And it works so well that when we look at the rollouts and we compare all the videos that were generated, we basically win like 98% of all rollouts. And the ones that we lose barely. So I think it's basically a free thing that kind of works on top. And this is also shown in our user study where almost 80% of the users prefer ours over the baseline. Qualitatively, let's discuss what happens. Now, in this video, you would see in the baseline, if you can see here that the arm completely dissolves here, and that's because it starts to have an error over here and it propagates until the end. Versus with our RL post-training, not only is the arm consistent, but you can also see that it does this like twice, it pushes the thing and it's able to replicate the baseline, the ground truth actually. This one is even more interesting because the cup again seems to just vanish. It's fully gone. And yeah, there is no task to be completed. But here, after our training, this becomes a lot more stable, and you can kind of see that the task can be recorded. Um, Again, similar things, the entire cup goes away, and it does appear later, but yeah, it's gone, and if the task were to place something like this, or were to check whether the object is being placed, you cannot actually measure that. There are other improvements as well. It's hard to see, but there is a better alignment between ours and the ground truth versus this, and you can see it when it goes to grab it over here precisely. Um, it's a bit hard to see, but there are other improvements as well with this RL kind of strategy. Some highlights, these are like some complicated tasks, including these that I showed earlier, were actually being generated with our model. And they work so well that you can kind of see that it's really hard to say that whether they're actually being generated by the world model. And they work especially for soft bodies, which are very, very hard to simulate. There are other ones like towel placing and kind of holding on the chips. So now I would like to jump and ask what a world model should know. We could see that videos are a good way to do, but there is an issue. And that is that these world models actually lack geometric understanding. And you can see that over here, that the arm goes behind the door, but because this model lacks this geometric understanding, it basically shows that the arm is hitting the door, and this deforms the entire door. So the question is, can we inject this 3D understanding into these robot world models? And that is what we address in our recent work, DepthWorld. This is a very, very fresh paper, not yet uploaded on archive, but it will be soon up there. To begin with that, we need to first augment our data because we don't really have that 3D data with us. And beginning with our input, which is basically these stereo vision cameras, we run a disparity model, and we can calculate like these really dense disparity maps. Then we do these like calibration, because even if you have depth per camera, you cannot really form a 3D scene until you know where the cameras are actually placed. And we do this consistency thing. And because we also don't have the ground truth camera poses to optimize for, we have to ground them to the robot. And the problem is that the robot itself has a lot of unknown parameters. So we basically run this joint factor graph optimization for all episodes of a given robot. So one robot might be present in like 9,000 episodes, and we optimized over all 9,000 episodes simultaneously. So this shows the animation of what happens. You can imagine that there are the two cameras, and you project from them, and you'll see that they don't align, and this gray is the robot. In the first stage, we basically try to align the two cameras, but now it's not aligned with the gray surface. And you can see that now we try to align with the gray surface, but it's quite coarse, and you can see it over here. And it finally does this entire learning, and it's very well fit to the robot. So yeah, over the entire trajectory, this is what happens. Now, compared to this previous effort, PointWorld, we are far better. On the external cameras, we are able to get almost sub-pixel reprojection errors. And for the wrist to external cameras, we get like 1 pixel. But also the other issue is that like the correspondences itself have an error of 1 pixel. So this is almost the lower limit of what's possible. This is the robot depth. We measure the depth error on the robot body, and it's like 14 millimeters, which is basically 1 centimeter over the entire surface. And our IOUs are also quite good. And you can kind of see it, like in the baseline, you can see that this is a robot, but the two projections are not at all on the robot, but in ours, it's quite well grounded. And this gives us this really nice 3D data set, which is of the robot doing quite complicated tasks, and you can see that it looks really nice, and we can do a lot more with it. Another example. And yeah, these black things are here because there are like shadows of the robot onto the wall. Okay, so from that, now what we do is we try to build DepthWorld, which is our world model. And what we do here is we simply take a depth depth maps and we concatenate them as images. We started with this because it's the simplest way to go about it without actually changing anything in the backbone. And we also realized that having this DPT head, DPT is a dense transformer basically that like recent models like VGGT use. Um, yeah, and we basically get this rollout, which kind of does really well. And yeah, now we basically are able to generate these metric depth values, but we find that by modeling depth, we can also improve our RGB metrics as well. And you can see some qualitative results here. It's the same one that I was showing at the start, but now you can see that in our case, it actually goes behind the door. Maybe I can show a few others. Sorry, I skipped forward. Yes. In this one, you can see it collides with the door, but here it's actually going inside. It also helps with object permanence. Like you will see that because this thing is white, it completely misses it, but it's there in the depth maps. And it actually ends up giving you these really nice qualitative results that I will, skip for the future. So now we can complete this and we can say that, okay, you could learn 3D videos as well, and that would improve downstream. So the outlook is one thing that you could do now is that given that we have an RL post-training thing and a world model that does 3D depth, we could use some 3D rewards, or we could do some better modeling with 3D, like VGGT or some newer architectures that are able to much better handle these things. There are some works like Gen 3R or Gen 3C that do these. More importantly, we could also do planning in these world models, and that was the entire point. Now that we have both a model that can simulate the geometry as well as do a long horizon, we should be able to plan in them. And finally, we can look at what are known as world action models. These are basically learned planners that couple with the world model. And basically, you can give them a text condition of to do something, and they can plan in the world model that they have learned. So yeah, the future looks quite interesting. And I would like to firstly thank my collaborators, Patrick, Yosef, and Vlado. And you can find their works over here. Thank you.